Okay, great. So thank you all for joining me today. This is going to be our first core study group on the diffusion model. As we know that this topic is relatively new, and what we have is a bunch of papers. So what I want to do this time is actually to have a more course-like experience by first going over the mathematical fundamentals for all the diffusion related stuff. So to start, I want to first go to our first topic, which is VAE. So, so why do we start here? Because later on, as we'll see, that the variational diffusion model, which is our first model, will actually be a continuation of this idea. So first, could anyone maybe tell me what's the motivation to use VAE? Yes, yes, to generate images with the help of a latent variable, right? So we have basically like two mathematical entities. One is the image and one is the latent variable. The assumption with this kind of model is that we have Z, which is sitting on like a dimension, like two different uh, different Euclidean space where we normally have dz, dz is less than dx, right? So we are doing some kind of compression, and then we're trying to sort of denoising, because Z here we assume normally it follows a normal distribution of 0 and 1. So the goal of generative model in general, like with the expression, for example, for GANs, is to estimate the quantity known as the density of the original data. But this is often a very difficult problem. So with VAE, we tend to focus on a different objective that is that kind of functions as a surrogate of this one. And the trick is the following. We start with the log of the density, and we introduce a arbitrary variational distribution QZ, which is chosen arbitrarily as like not independent of the PX. So we can sort of write it in this way. And then we can invoke the product rule in probability to decompose this term further by using the joint distribution over the, sorry, um, using the joint distribution over the posterior distribution of Z over X. And we do some sort of tricks to write the variational distribution here. And we rearrange the terms a little bit to obtain two terms. The first term is the joint distribution on top and the variational distribution at the bottom. Second term is the variational at the top and the true posterior distribution at the bottom. So this term, if we treat like, if we like factor them into two terms, we got, this one, which is the joint over at top and the variational at the bottom. And the second is actually, we know this is the KL divergence of QZ, PZ, right? Because by Jensen's inequality, we know that the KL term is always non-negative. So we can conclude that the log PX is greater or equal to the first term here, which is called evidence lower bound or elbow. So in the traditional variational inference with so this, you mean the first line? The first line is basically a trick. It's basically saying that like if you expand the expectation, you got an integral, but the integral with respect to z. So you can sort of put px directly out, and the integral just leaves you one. So that's why you can write it this way, because the distribution of choice, the variation distribution has nothing to do, is independent, let's say, has no information sharing with the original PX. Yes, right. So this one is clear. Now let's go to an extension of this one. So the second model we're gonna talk about is called the Markovian hierarchical VAE. So the idea of this one is instead of using one latent variable, we introduce a bunch of sequential latent variables. So this one goes like this. So this is basically like a Markov chain, right? Originally, we have X that's probably sampled from P data, and the ZT here is sampled from a normal distribution of 0, 1. So with this one, we have the following notation. We say that the forward process is a distribution Q and the backward is distribution of P, which agrees with the VAE notation because in the VAE, we sort of seen the posterior distribution of latent using Q here. So we can apply the same logic here. If you look at the elbow, um, if you look at the elbow, this is the objective used in variational inference. So there are two terms that we care about, we want to estimate. First is the joint distribution of X and all the latent, and the second is the posterior distribution of the latent conditional on X. So in this case, it becomes P of X comma Z 1T, right? That's the joint distribution. So how do we write this, right? We can factorize it easily because this is Markov chain. So the joint becomes, let's see. Yeah, the joint is basically, we start from the end, and we do a bunch of, let's see, P of Z T minus 1 ZT. So T equals 1 here. And then in the end, we have a X C1, right? That's the factorization of the joint. And then let's look at the factorization of the posterior latent. This would be Q of Z1T over conditional X. And this would give us the forward process, which is Q of Z1 conditional on X times the product of ZT minus 1, right? So these are the two formulas we can use to represent the two quantities of interest in the elbow for the Markovian HVAE. So before we go to write it in the elbow, let's actually jump to, sorry, how do I? Okay, yes, thank you. So let's actually directly jump to the variational diffusion model, because this is actually same as the Markovian HVAE, with the difference of instead of using latent, you kind of do this. So the difference is that normally we have all the z's in a latent space of dimension dz, and x is like in the dimension of dx, and we have dz is less than dx because we want to do some kind of encoding decoding scheme. So with the variational diffusion model, we sort of put all the variables in the same ambient space of RD. So all the xi's belong to the same space. But we follow the same convention of using a forward and a backward process for this model. And we can have the same factorization. In fact, the factorization becomes even easier if you write it out. So for example, the forward would be Px, which is defined to be P of X1T. And we can directly plug in the previous formula, which is pxt times tt. Right, that's the forward. We sort of get rid of this term because there's they're all x, right? And then we can also talk about this one here. And it becomes very easy, just one product term of everything. Let's see. I think here is a mistake. Yeah, this one should be here. Right. So, sorry. Oh yeah, there's no Z. Sorry. There is no Z. So now let's write the elbow. Yeah. 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 In this model, they're all in the same dimension. It's just like imagine that you have image, you're applying some Gaussian perturbation to the image. Doesn't change the dimensionality of your data. Yes, with Z you have different dimensions. Yes, as a special case, right? So VDM is like a special case of the second one. All right, so let's write down the elbow. The elbow, like we know, it's just the expectation of the posterior, sorry, no Z. Posterior of x1t, x0, and then we have a log term. At the top, we have the join term, which is in the bottom, we have the posterior term. So now if we look at this formula, like what would be a naive way to optimize this, right? We can sort of parameterize the P's and Q's with two neural networks as people do in VAE. But here the expectation is like you're taking expectation with respect to a distribution that can be factorized into multiple random variables. And they're sequential. So naive solution, I would say, could be a sequential Monte Carlo, right? But the problem with that is you have a high variance when you're dealing with the Markov chain because at every step of the Markov chain, you do a sampling. And the variance builds up pretty easily when you have a long chain. So we definitely need to do like more processing of this formula. And in fact, we can write this one in a much better looking way by breaking it apart. We know the product inside is like, if you take the log, it becomes sum, right? So if you put them apart, you can sort of deal with each of them individually, if that's possible. So here, we want to do two things. So we want to break the expectation apart. And we also want to get, like people usually do in this kind of literature, we want to get a bunch of KL divergence. Like hopefully we have some, and you know, like KL divergence, it's normally like written as like a KL of a QP equals expectation of Q log QP, right? That's the definition of KL. So we want to write this one in a way that Q appears above and P appears down, you know, something like that. But as you can see here, we have P at top and Q down here. So we want to sort of use some tricks to make it into the way that we like. And there's one trick that we can use, and that is the Bayes rule. So what we use, what are we doing here with the Bayes rule is the following. Okay. So we can write Q of xt minus 1 equals Q of xt minus 1 xt times Q of xt over Q xt minus 1, right? That's the Bayes rule. Now, what's interesting is that we have a Markov chain. So this term is equal to the one above, right? Agree? this one equal to one above. And we can apply the conditional base rule, or if there's a name for it, you just add a conditional term to each of the term on the right. Right, so with this formula, we can, so we have this one. And what we're gonna do next is we're gonna swap it out to here. So note there's actually a, note that there's actually a caveat of applying this formula, because when we conditional x0 here, you look at this, if we take t equals 1, then we have two x0s. So if you really want to apply this formula, we start with t equals 2. So let's take a look at the elbow again. First step, so step 1, we're gonna break the product terms of from t to t big T to from here, and then the additional term, and then additional term. So that means we write the elbow as, so for now I'm just gonna abbreviate it with QZ, and then we don't change the top first. We're just gonna worry about the bottom for now. So P of xt minus 1 xt, and at the bottom, we're gonna break it apart into two parts. First part would be when t equals 1, which is we have a q of x1, x0 times product of this, right? So the second step would be to use the base rule. Use the base rule to break it apart. And that means we have, so this one here equals, we have the same thing. Let's first just ignore the top part, right? Top part ignore. And we apply the base rule for each of the terms. And that is, so what do we have? We have q of xt minus 1 xt x0, q of x t x0, and the xt minus 1 x0. So if we look at this term here, we actually can see something very interesting going on. Because there is a product here, and we see that this term sort of is always ahead of this term by 1, right? Because if you say like t equals 1, we have at the bottom, t equals 1, we have at t equals 2. At the bottom, we have q of x1 conditional x0, and then top we have x2 x0. And if t becomes 3, at the bottom we have q of x2 x0. So they always lag each other, and because it's a product, they cancel each other out. So that makes this term here becomes so the first term doesn't change. It's the same thing. Now actually now let's look at the no, let's not write it back. Sorry. Okay. Yeah. So I think yeah, and xt x1 x0. So are you talking about the one outside x1 x0? Mm, yeah, yeah, yeah. Yeah, it's gonna cancel out, but it's not gonna hurt us actually. So we cancel, we write it this way. We have this term intact, and then we have two terms. The first term would be, as Professor mentioned, will be later on canceled out, but for now it stays. Uh, it is when t equals 2, we have x1, x0 here. And the other term is when t equals big T, we have big T, x0, right? And we can cancel this one and this one. So that makes our bottom part to be just, it's kind of messy, but um, yeah, let's just rewrite the elbow here. So we write the bottom part first. We have this one, and we have this one, right? And at the top we have um, and pxt. Mm, okay, so do you guys find any mistakes, because this doesn't look too right to me? But yeah, let's continue and see what's going on here. So first we can break it apart into different terms by first looking at this term is a pxt and the qxt. We can take this term out. This is what they call as prior consistency term, right? I think so, something like that. So and notice that because we already know what is xt. Xt is the normal distribution of 0, 1, right? This is like by definition, we want this property in our model. And then in the variational diffusion model, actually Q does not have any trainable parameters. Q is actually defined, as I will later say. It is actually defined. So this term, there is no trainable parameters. It does not affect our training at all. And then we can sort of break the product into two parts at the top. Here at the top, we have different indices, right? T equals 1, t equals 2. So we can break the top part into p of x. So we can take this one out times p of xt minus 1 xt. We can make it this way, and then we will have a summation of expectation, where summation is from t equals 2 to big T. And inside we will have at the top the px minus 1 xt term, and the bottom this one, right? And then that's the part I think there mistakes happen, because in the final form there should be another term which is actually log of um oh wait a sec. Okay, actually it's correct, because if you look at this term, what is this term? Oh no, let's see. P P is actually not x1 0, it's P is the reverse process, so it's x0 x1. I write it wrong somewhere, but what is this term, right? X0 is the original image. X1 is like our first latent, if you look at it as a VAUA. This is actually called the reconstruction. Oh yeah, there's a P, sorry. Yeah, there's a P. So we have three terms. one reconstruction, one prior consistency, and I think this one they call it. I actually don't forgot what they call it. Do you guys have a good idea what this term means? Right, denoising matching term. All right, denoising matching term. So what exactly is this term though? Right, we need to do some further decomposition. So the last step is to turn everything into KL if possible. So apparently the reconstruction term is not a KL divergence, right? Um, let's actually look at how about the prior consistency term? I mean, it doesn't really matter for our training, but um, is it a KL divergence? Turns out it is a KL divergence because as I noted, the Q was like this one. So there's no Z, so it's like the Q is this one. And if we look at the prior consistency term, the only random variable that we have with respect to Q is xt. So if we take the expectation, we can just keep the last term. So the first term is actually just the expectation of Q of xt, x0, and we can sort of rearrange, use a negative here, and we have the Q above, and we have the P below, right? So in a way, this is the KL divergence of negative KL divergence of Q of xt, x0, xt. So this is, so the first term actually gives us some insight what it means. It means there's a, what is the difference between the distance between our prior distribution and this term, qxt0 here. And now let's look at the denoising matching term by looking at one specific value of t, right? We have, again, this would be xt, x0, because all the other random variables disappear when we only care about t minus 1 and t. So actually, this is a not, it's a joint because we have two. We have both, right? We have two here, two random variables here. So that would be xt minus 1 xt and q of xt minus 1 xt. And then we take the negative sign again and flip the q's and p's inside, right? So the next thing to do is to simply try to figure out what is the relationship between this term under the expectation, the q joint xt minus 1 x0, and the term inside the bracket q xt minus 1 xt. So so I think there's like one additional step that we did that I kind of forgot to put here, is that we turn it into, we kind of use this conditional base, right? So I think the Q is actually not xt minus 1 xt, but there's a x0. Yeah, there's a x0. So there's actually x0 here. I think I probably forgot to write it somewhere. It's probably here, I guess. Just try to make it consistent. There's x0 here. So we can actually kind of look at what's the relationship between these two, and it's very easy. What's the relationship? It's just so we can write it simply as xt conditional x0. Then we have what is oh no, sorry. We have the KL divergence of q of xt x0. Wait, no. sorry. I'm skipping multiple steps. So we write this as two expectations. First is the xt x0, and the second is xt minus 1 xt x0. Can you see why this is the case? Because of the factorization. Yeah, I guess. So the inside stays. We take a negative sign, so the q goes up. And the p goes down. And then we can just do the KL divergence. So this is just a xt x0. Inside we have KL divergence of q xt minus 1 xt x0 and the pxt minus 1 x0. So again, this term is the expectation of a bunch of KLs. So that's what this term means. Yeah. Any question regarding the derivation?
I see here we have it's like for the standard being used, we also have the prior stuff, but we also have the prior action.
Yeah.
Just the summation for like that's the action.
Yes. And that term exists because you have a Markov chain, right? The VIE is basically a length one Markov chain, so it doesn't have any kind of intermediate terms. And I think the reason why the derivation exists in the first place is because we want to understand why we call it, we give the terms these names. And because they are all like KLs, the KL divergence, they're kind of saying if we want to minimize the loss, we're trying to make the forward and the backward process as similar as possible. I think that's what it is, what it implies. Yeah. So I think right. I mean, implicitly xt is there because in order to get x1 from backward, you need to start from x50, right? And you need to go through the entire reverse, what they call the reverse diffusion process to go to x1. Like, so here I think
one is right next. So once we know x, but can you say the reverse process forward is a Markov chain? But it is necessary that the
no, reverse is not necessarily, yeah.
Yeah.
Reverse is normally parameterized with a neural network. So it doesn't have the assumption of the Markov property. Yeah. Q, yeah. Sorry, no, reverse is actually P in this notation. Yeah. Q is the forward. All right, so let's go to the next part, which is the assumptions made by VDM, simplifying assumptions. So VDM make the following assumption about the forward process Q that makes it a much easier problem. So this is the assumption. The Markov chain of forward process xt minus 1 follows the normal distribution that has a mean of, I think, this one, and the variance is this one. Right, this is the, which one? Oh, this is, Yeah, this is alpha t. This is alpha t. So actually, this is just minus alpha t times I as the variance. So this is their assumption. Or like this kind of model is normally known as a linear Gaussian model, right? And we know that the good property of normal random variables is that we can use what is known as the reparameterization trick. That is it's kind of a term people use to control the amount of noise you want to inject at each step. If you have, for example, if you have a large alpha t, what happens, right? If you have a large alpha t, that means the variance of the injected Gaussian noise is small, and effectively you have a smaller injected noise. If you have a small alpha t, then you are injecting a large variance noise. So yeah, it controls the mean because as you see, we want to have, so we want to have at the end x big T to be this. So we need to do two things. We need to decay the mean, right? We need to decay the mean to zero when this process converges. We need to decay the mean and we need to force the variance to be close to one. So you can sort of imagine that I think the alpha t would start, if alpha t equals zero, then we have a zero mean Gaussian, right? If alpha t equals, and if actually, if alpha t, I just write it, if alpha t equals zero, we have a transitional probability of directly following this, right? Alpha t equals zero, yeah. So you could imagine that maybe they start with some big alpha and they schedule gradually decrease alpha t following some geometric series or something. Yeah, but first let's go to let's go to the derivation, which would actually, because you see our objective is to maximize the elbow, and there are several terms that we need to figure out. For example, what is this term? What is this term? We can simply use a neural network to do this. But for the Qs, you know, the VDM provides some answers. They actually have analytical forms. And the reason why they have analytical forms is because of this linear Gaussian assumption. So what we're going to do next is actually to derive why this is the case. So the first thing we're going to use is the location scale family distributions property, which is we can write xt to be alpha t square root plus this one times a random variable for, how do you say this one? Actually, let me give a different one. This one, this is epsilon, right? Okay, so and epsilon is following a normal distribution, right? This is the property of the normal random variables. And then we can write it recursively, right? We can say xt equals alpha t of alpha t minus 1, xt minus 2 plus 1 alpha t minus 1 plus this one, right? And at each step, we sample independent standard normal random variables. So if we break it all apart, what are we going to get? We are going to get alpha t minus 1 inside t minus 2. And then I'm just going to skip the next step. It follows the property of normal random variables. If you want to combine a linear combination of two normal, you take the sum of their the mean as the new mean, and then you do the sum of the square and then square root to get variance, to get standard deviation. So this becomes 1 minus alpha t minus 1 square root And we can follow this process until we reach x0. So what we have is actually xt equals product of t I equals 0, alpha 0, alpha I. Actually, this one is this index start with 1, x0, and plus 1 minus product alpha I. Yeah. So if we call this one alpha t hat, and this one would be 1 minus alpha t hat. So we have an analytical form for the transition probability of this one to be a normal distribution of xt whose mean is alpha t and whose variance is 1 minus alpha t. Right. So this allows us to express the terms in the elbow because let's see. Yeah, this one basically allows us. I think it's a little bit too cluttered to go through everything, but you guys should trust me that once you have this, you can express any cube, because the property of normal random variable is very nice. You do linear combination, marginalization, conditioning. They're all they just give you normal back, and the KL divergence between two normal is analytical. You have a formula for that. Right. So I think. So yeah, so basically this gives us a way to express the forward process. Now what's interesting about this process, I just want to see like a side. So we know that xt equals alpha t xt minus 1 plus 1 minus alpha t. Wait, this is delta epsilon. So what do we do here? We actually, you can do the following trick. Xt minus 1 equals this one minus 1 times xt minus 1 plus this one. And you can take a leap of faith to look at this as if you have a continuous process. So this would be xt minus, actually let's write it this way. Let's do xt minus 1, xt, and yeah, like this. So here's xt plus 1 minus xt, and this will be xt, and so on. So you can sort of make it a continuous random variable by viewing it as t plus delta minus xt, and then here you have sort of like f of xt times delta, and you have that's just I think this would be a Brownian motion times drifting term, and then you can. So what I'm trying to do, the motivation is to turn this discrete stochastic process into a continuous one, so that we can motivate the notion of a stochastic differential equation. And the way you do it is you take infinitesimal steps in time, and you sort of take the limit as t goes. So you divide by epsilon, and then this one goes out. Yeah. So this is a very sloppy thing here because yeah. So the idea is that when you have this, yeah, F and G, yeah, just basically this is you can see this whole thing as a function of xt, right? As actually a linear function. like if we really want to go that route, is actually pretty difficult. Um, Here, I just want to provide a high level idea of, yeah, yeah. A discrete step of one, yes, we go back. But then, yeah, yeah. Yeah, it's easy to reason about the left-hand side, but the right-hand side is a kind of difficult to reason about. Uh, that's why I just abbreviate it as a function of xt. Um, yeah, it should contain the alpha t. In fact, it should follow the linear form because the original one is a linear function of xt. Yeah, gt would actually be a scalar function. You give it a t, returns a scalar. Yeah, and then the bt would represent, when you have an independent random variable, and you sort of try to formulate it in the this kind of stochastic differential equation language, you describe it as a Brownian motion, which is bt. Yeah, it's epsilon. But here, imagine that you are injecting two normal noises at two like a time t1 t2, and if the difference between these two time difference is very small, the Brownian motion is actually trying to measure how much how much sort of noises, like a difference in noise you have in this infinitesimal time step. So yeah, so this is just this is actually something I'm still studying, but this form is actually well defined. Um, I think this is the same motivation people use to neural these. Because originally you have a discrete process with a finitely many steps. So theoretically, people would say that if you have a continuous process, it is mathematically more expressive than the discrete one, because you can arbitrarily choose how small your step size be, and then, for example, infinitely wide or infinitely depth, something like that. Yeah, right, right. So the notation for this type of thing is, you have, in the end, of course, this is very bad. I just want to throw out the idea because I actually kind of lack the rigor right now to write everything in detail. So you just have to trust me that this can be written as this plus GT times BW, where this one is called a Wiener process, which is an infinitesimal Brownian motion. Actually, it's a really terribly stated, but yeah, and this one is called a diffusion term. This is called the drift term, and this is a stochastic differential equation. This is what happens when you try to make the discrete Markov chain continuous. And in this case, this one is a linear function, and this is a scalar function. And in this particular scenario, we call the system, this equation, a Langevin equation. So you can sort of see that a natural extension of this variational diffusion model to turn it into a continuous version is to use the forward Langevin dynamics to perturb it. I think this is actually something that was explored in a paper. Yeah. So now we know we fully define the forward process. What's left is to learn the reverse process, right? We know that we have this kind of process that gives us normal in the end, and here is the data. We can fully realize the Qs, but the generative task would rely on the p thetas, right? So what would be a strategy to learn the p theta? Now of course we utilize the elbow. Then the central term in the elbow would be this denoising matching term. So this term actually says that we want to have this and this as close as possible, as we later derive there, the KL divergence. And this one, so we know that this one is a normal. So naturally, a very easy design of neural network is to model this one as a neural network that has a parameterized mean, and we can actually simply just use one minus. We can simply just match the variance. So this is one strategy. It's actually the simplest strategy. We match the variance for forward and reverse process, and we try to match the mean. So if we adapt this method, this is called the mean matching. So learning the reverse denoising process. So first strategy is called the mean matching. And then there are some other variants of like, depending on how you write the formula of the mean, it actually can turn into something called a noise matching. And the score matching. So the score matching is actually very, very interesting. It's gonna tie us to another perspective of the diffusion model. So now I actually want to go to my slides because I think we've done enough derivation. Yeah. Thank you, Shitang, for the iPad. Yeah, no need. Okay. Thank you. So I'm gonna go to my slide. I think we've already finished all the hierarchical Markovian variational inference part. Just want to show you for the reverse process. In fact, I think it's probably better for me to write on the board, because if you just look at these derivations, you can easily get lost. But there are more tedious ones coming. Like if you want to learn the reverse process, you want to match the mean. And then you can use a bunch of mathematical tricks to write it in different ways. First one is to write it in this way. And then you start with the mu's, and then you end up with the x. Second one is you end up with this form, and so on. In each case, you parameterize the quantity of interest with the neural network and to do some training. No. I don't know. I don't know. I think this is not very important, to be honest. These are just normal random variable manipulations.
There's like all these equations are actually proven in there. So I don't know if we can continue this. So
I'm sorry, it's no. All right. All right. Okay, so yeah, I think we go to the second part, which is also very important because this is a technique that's used a lot in score-based methods. Something that we actually went over before in our previous reading groups. So we know that in like energy-based models, we like to model the probability distribution with what is known as an energy function, right? And the reason why we want to do that is because we kind of want to, ignores the requirement of the property of a probability density function, which has the requirement of, for instance, the integral has to be 1, right? But if we would just model the F part, which they call the energy function, you can use an arbitrary neural network. But the problem is that there's a normalization term Z here, which often make this problem intractable. So however, exists another quantity in probability called the score function. And if you look at this, the gradient of the energy function actually equals the score function. Score function is defined as the gradient of the log density with respect to the data. So this allows us to sort of think, wait, so if we can, what if we can use the score function, right? Because the score function is kind of like a bridge between the fully expressive energy and the highly restricted density. The way to do that actually comes a long way. Early on, it is the notion of a Hamiltonian Monte Carlo. Why? Because this is one of the methods that can can be reliable on, using gradient information to sample from a probability distribution that is unnormalized. I.e., you can deal with sampling from the density, even though you only have access to the energy, right? This is the whole idea of Bayesian posterior sampling, because the Bayesian posterior term, you have that normalization at bottom. So the Hamiltonian Monte Carlo makes use of the Hamiltonian system, which has this term called Hamiltonian, which is H. It is the sum of potential energy and kinetic energy, where the potential energy is normally the model of our data, a function of the density. And then the kinetic energy is like something by design. People want to inject momentum to sort of sampling from different energy levels. Yes, yes, exactly. So that's what I'm gonna say next. So I think we can safely go, skip all the HMC stuff and go here. So yeah, yes, I think we did in one of our reading groups. We did go over the Hamiltonian Monte Carlo. Yeah. So if we actually, you see that the Hamiltonian Monte Carlo, if you want to solve it, you rely on some numeric ODE solvers. And there exist different ones such as the Euler solver, the leapfrog solver, and a special case of the leapfrog solver, which takes one leapfrog step and taking designed, kinetic energy that consists of independent normal random variables. You get the Langevin equations or the Langevin system. And if you look at these two formulas in the Langevin system, actually there's only one gradient term, which is the partial derivative of the potential energy with respect to Q. Whereas if you look at the Hamiltonian system, there are two different types of gradient. So in this way, you can sort of write the energy function as a gradient of the data, because your potential energy is a function of the density. So with some mathematical manipulations in later papers, they're able to give this kind of formulation for the Langevin dynamic sampling. This is actually a paper in I think Bayesian deep learning. They claim that if you follow this Langevin dynamics with access to only the score function, you can guarantee to sample from the original density. So this xt and xt minus one would converge to sampling from the density function under some regularity conditions and under when the epsilon step size goes to 0.
What we have done so far is try to use the model from
yeah.
Although it generates with some findings, and then want to kind of elbow so we can really optimize the findings.
Right.
Okay. And then, so still, okay. Then we come to the something connection system. So what's the connection that our model that feeds dynamic system?
Right.
The still.
So yeah, I think
From there to here, still some gap, but
right.
what's the connection?
Yes. So the reason why this one is introduced is because this is like the mathematical background for another perspective on the diffusion model. So early on, we talk about the variational diffusion model, which takes the perspective of a like a variational inference perspective. The second perspective is called score-based generative model. And in this case, they're directly trying to model the data distribution. And because they want to use the energy function and they don't want to deal with normalizing constant, they end up using rely on the Langevin dynamics by using the score function. So
So here you can make what was the tax or the connection? In order to be the setting.
yeah, so this part I think is completely independent of the model. Now here we are actually talking about the algorithms because these algorithms are what required for us to understand the model. Actually haven't gone into the model part yet.
You're saying this is the
Yeah, yeah.
connection.
The connection is this algorithm is used in score-based models, score-based generative models. Yeah, maybe I should have given a better, like a bigger picture in the beginning. Yeah. So yeah, but this is basically just introducing this algorithm. Later on, I will make the connection.
Okay, so when it is score-based model, what's that related?
It is related, but it's not directly related. You have to sort of reason about how it is related when you look at the formulation of a score-based generative model.
Okay, we talked about the noise.
Yeah.
So then for the here, that this is
Right. It is.
about matching part.
No, this is not about matching part. Because you see, with the probability generative models and density estimation task, you have two ways to do it. One is to use variational inference. One is to use sampling, right? That is the two common ways.
You jump out of the
Yeah, I'm jumping out of the VI, now going into sampling.
because I think the last time the reading was about Bayesian.
Yeah,
So
yeah.
we're talking about
Yes.
maybe the leap frog is I think for the control was the villain or the Poland. So okay. Here the goal is try to maximize it here.
No, so the goal is always to estimate the density or do generative modeling, right? So, right. So variational inference, the goal is to essentially is do maximum likelihood.
Yeah, maximize.
Yeah, the original goal is to maximize the data's density, but we cannot do that. So you introduce a surrogate called the elbow. And to maximize elbow requires to maximize the to minimize the KL between the posterior and the variational posterior.
So right now you want something.
Yes.
The first part is conversion.
Sampling, yes. And they're trying to solve the same problem. And actually later on you will see that even though they start with different principles, they end up to have very similar forms.
Obvious sampling.
Right, so
I didn't
part is started from a variational or encoder perspective, but this one I would say is started from like the HMC is like the beginning of the way to go to the stochastic differential equation part of which also can be interpreted as a diffusion process. So like the first part of the presentation is about how to get to the diffusion process using VA, and this part is how to get to the diffusion process from HMC to SD to diffusion.
Okay, that makes sense.
Okay.
So for VAE, it's like the first discrete process, and then from the discrete process, and we go to the here's like HMI.
Yeah.
In the end, it will be the
Yeah, in the end, it's like HMC would also like go to no stochastic differential equation, which is now introduced as like score-based
Score-based generative model.
that score-based generative model, which score-based generative model also can be used like using the stochastic differential equation, which can also be used like diffusion process. So score-based generative model finally reached to diffusion process, and also VA goes to the same direction. So they meet at the end. But
the beginning of the version makes lots of sense, but we just
Yeah.
do this kind of thing, step by step, with like a small step. But here, the economic access is quite important to our
Yeah, it's a
generation.
it's an independent like generative modeling. They always have these two ways to do approximate inference, right? Either VI or sampling. And with sampling, you normally deal with this unnormalized energy. That's why they invent all these algorithms. HMC is one of the algorithms. Special case is this Langevin dynamics, which is used by score-based generative models.
So I guess if we go back to data is somewhat that data is funded on the one point,
Yeah.
right? So and then we follow one.
Oh, so yeah, so yeah, so I think it may be confusing to put HMC here. What I try to do is actually just to show that there is an algorithm that can help you to sample from P with only access to F, because that's essentially what the HMC is doing. You don't worry about this normalizing term. We want to sample from P theta, or PX. Yeah, basically we want to sample from PX. Let's not just ignore theta, let's just say PX. And then how do you do that if you don't know it, right? And do you, for example, what if you know the energy function, or you know a unnormalized case of P? The way you do that is to use HMC or Langevin dynamics.
At least I know the
All right, so a key term in the Langevin dynamics is this score function. We need the score function to do the sampling. So that's why there are like score matching algorithms that people use to estimate the score function. The objective is actually very straightforward, right? It's called the Fisher divergence. You minimize, for example, you create a neural network to model the score, and then you minimize the L2 distance between them, expected. And then, however, you don't really know this term. So how, for example, you don't really know this term, right? So it's not like you have a supervised learning task where you have ground truth. We don't even know this term. How do we even estimate this loss? So this paper in 2005 used some tricks in calculus to show that this loss function, this objective is actually you know equivalent up to a constant difference to this following one. So it completely gets rid of the log the ground truth score function and replace it with this term, the trace of the Hessian matrix of your original data density, and then the you know the norm, the two norm of the score. So later on, there are some further works that try to make this one more scalable because the Hessian is a really giant matrix. So they used ideas from denoising autoencoder by postulating that the density, the score function is a vector field such that if you fall out of the distribution, it should point to your distribution. And they use this kind of denoising distribution to approximate the score function. And then later on, there's this slide score matching, which used some other random matrix theory to derive the same kind of objective. So I provide a good link on this. I think this is a very good YouTube video by Song and Armand on this score matching algorithms. So so the dynamic systems that people use to sample, for example, Hamiltonian, the Langevin dynamics, they're kind of sampling from the static distribution, right? However, in diffusion process, as we see early on, with the variational diffusion model, we kind of want to change the distribution into some prior distribution that is tractable, for example, a normal distribution of 0, 1. Right. So, and as I showed before, if you make this process continuous, this perturbation process continuous, you get what is known as the stochastic differential equation. So next, I want to introduce, briefly introduce what is a stochastic differential equation. So first, we kind of review the ordinary differential equation, which is this very simple system with an initial condition, and then you represent the gradient with respect to time as the derivative with respect to time as a function. And we know that under some reasonable assumptions of the of f, actually the type is f, every ODE has a unique solution given its initial condition. ODE is a very well studied and very I guess simple model. So now what if we want to add some perturbation to this dynamical system? If you compare this one with the previous one, we just simply added additional psi t, which is a random noise, to the derivative. So this, yeah, the GT is called it governs how big is your noise. There's no, yeah, it can be actually something else. It can be more complicated than a scalar. The easiest case is a scalar. Yeah. Right. So just like the ODE solvers, the SDE solvers also exist, and they also try to discretize this one. So I just want to give a high level about these three kind of mathematical models for dynamic systems. So ODEs often appear in the context of a conservative system where heat is not introduced. For example, in classical mechanics, in the Hamiltonian system, you have Hamiltonian, which is invariant. There's like the sum of kinetic energy and the potential is like a invariant across time. However, when you introduce heat, it becomes different because heat is this quantity that's kind of it's a macroscopic quantity that's describing the behavior of a bunch of molecules, and the molecules are microscopic, so you cannot really quantify them, at that level. You have to use some statistical quantities. and that's why the language of stochastic process comes in. So when you're thinking about a diffusion process, for example, you look at this image in the bottom. You have a bottle of water and you inject some ink into it. The ink particles will go through this Brownian motion and it will dissipate into the water, reaching this final equilibrium state. And if you think about it as a probability distribution, what you have is you have at the start, perhaps a Dirac delta function, right? You have a point density, and then it goes through this whole process of diffusion, giving you a uniform distribution in the end. So you can, so again, there are like two ways to think about it. One is you reason about it purely in the language of distribution. You started with a distribution, you go through a bunch of deterministic transformation, it returns you a distribution in the end. That's one way. This way is how PDs view diffusion. And then there's another way, which is you start with a with a deterministic quantity and you inject noises, which is basically the SDE way of looking at things. So here is a definition of the SDE. Right? It's basically the same way written before. I just give the terminologies. The FXT is called the drift and the GT is called the diffusion coefficient. The DW is infinitesimal noise called Wiener process, which describe a Brownian motion. So the mathematics for this one is very advanced. It's actually really, it's actually not really easy to formulate it, clearly without some background. So we can simply, for now, have a conceptual understanding about it. Yeah, and if we discretize the SDE and so what I try to do at the bottom is basically trying to recover the variational diffusion model that we did earlier. I think it's just I think I've already done it on the paper, so we can simply skip this one. So the forward SDE is basically trying to diffuse the image with the Q direction. Try to make it continuous by perturbing it with a stochastic differential equation. And then a very nice property of SDEs is that they're actually some of them under some regularity conditions has reversible SDE. So if you have a forward stochastic process, you can actually get its reverse stochastic process. So this corresponds to in our early VDM model, the forward pass and the backward pass. And this is the form of the reverse SDE. And we can already see that the central term here is the score function. That's why the score matching algorithm comes very handy. Once you know the score function or you get an estimate of it, you can do this reverse SDE following this update. So yeah, there exist numeric solvers for SDEs. You simply follow the ODE solvers and you try to carefully add in some noises, depending on the scale of the stochastic process. So they're like the first order solver, the Euler solver, which in this case is called Euler-Maruyama solver, and the Runge-Kutta solver, which is the multi-step solver that was used ODE, also has this stochastic version. So in the end, I just want to comment on why the diffusion model is such a powerful model. As we know, this model currently in image is the state of art and it's actually outperforming GANs. And it is, I think, one of the rare examples where the mathematics actually works, right? Because a lot of time you have very nice math, but when you write it into the code and you run experiments, it gives you really poor results. So of course, why this is powerful, the answer is open. There's no definitive answer on why this is the case. I think people often say, give some heuristic level justification of why this is the case. So perspective one is from the score-based perspective, because we know the score functions are modeling the energy function. And the energy function is a much more expressive function than the density function. And as the score-based generative model paper shows, the Langevin dynamics has a good mixing properties if you inject different scale of noises to the process. And then the second perspective is perhaps that we are doing this continuous perturbation, so we have infinitely many representation of the data. So so that perhaps makes it more powerful when you are doing it reverse in the reverse. So yeah, so this is basically, I think, my understanding about why this is the case. But if you have some ideas, please do share with me. I'm also very curious about why this model works. So I think there's a very interesting direction in research related to our primary interest in graph. So I think, yeah, recently there has been some papers about applying the same idea of diffusion on graph structures. So they're like, we have already know that the graph convolution can be actually viewed from the perspective of a heat diffusion, right? The famous heat kernel that people use in the graph diffusion is actually a stationary distribution of the heat equation. So so that paper at the top actually shows a connection between these two kind of models. And then we know there's some cases where the graph topology is not really good enough for the learning task, which I'm actually gonna introduce next week about graph rewiring related to this problem. So as we know that the diffusion process, the stochastic diffusion process kind of tries to destroy the data's original structure and then try to reconstruct it. So it is kind of similar to autoencoders in that way. And we have like autoencoders for graphs, but the objective, of course, was to reconstruct the original graph. What if we can apply the same idea of SDE on this graph or autoencoding, right? And there are already some papers working on that. And I gave some examples in the bottom, which could be good references. So the first paper is written by Song and Erman and Daniel. They try to apply, the idea of score-based generative model on graph, do graph generation. And then in ICML 22, there is already papers that try to apply SDEs to do graph generation. And I think there are several papers recently on open review for iClear 23. So I think in my perspective, this could be an interesting direction of research. Yeah. So I think that's everything I have today.
Great. Thank you.
All right, thank you. How do I stop recording?